All right, we're going to take a look at derivatives of inverse functions. Okay, and these steps right here just kind of guide you through what we're going to be doing down here. Let's look at example 1. All right, it tells us that g is the inverse function of f. Sometimes they use words, sometimes they use symbols. All right, anyway, that's the connection. G is the inverse of f, and 2, 3 is on f. So I guess 3, 2 is on g. Find the value of g prime of 3 given this function. All right, and then following the steps up above, what we're going to do is we're going to find f prime, plug in 2, reciprocate, because that reciprocal slope would be the slope on g at the inverse point. So we have the plan. All right, once we differentiate, we're going to plug in 2. Two squared is 4. 4 will divide with 4, so I'm left with 3. 3 plus 1, I'm going to have a slope of 4. That's on the f graph. So the reciprocal of 4 is 1/4. So my reciprocal slope is 1/4. All right, another example, number 2. Let f be the function defined by, so I have an equation. Okay, here, not words but symbols. We have a relationship of inverses. 1, 2 is on f, so 2, 1 is on g. So let's find f prime, plug in 1, and reciprocate. Easy enough. The slope is 7 on f, so the reciprocal slope is 1/7. So g prime of 2 is the reciprocal of f prime of 1. So g prime of 2 is 1/7. All right, we're going to go to note card number 17. All right, we're looking at natural exponential functions. All right, so a little bit of background right here. All good information that you should kind of linger on, look on, read on. Let's find the derivative of these functions. Just a review of those rules. All right, bringing in d over dx, we're going to have the rate of change of y with respect to x equals, this is going to be the chain rule. Derivative of e to the u is just itself times the derivative of the exponent. I'm sure you could have done this all in one step, found that derivative, you probably got 2, and then you could put it in front here. That's fine, do it in one step, but for those more complicated problems, it's kind of nice to have the rule, the formula that we could follow. Like example B. Okay, I'm going to find f prime of x, but I think to help me get ready to do that, I'm going to first rewrite the exponent. I'm going to bring the x out of the denominator of the fractional exponent. So the derivative of this function is itself. And in that case, I probably would leave it as -3 over x times the derivative of the exponent. This is a better form for the derivative. Power rule. Positive 3x, drop the exponent by 1 to -2. You're done, finished. You could clean it up, you could rearrange it, you could rewrite it. Okay, kind of studying what belongs on top, that would be the 3. The x squared would go to the denominator, and so would the e to the 3x. Again, this line's fine here too. All right, let's take a look at number 2. All right, this is kind of an interesting one that uses the formal definition of a derivative. Okay, our function is e to the x. It's asking us which of these forms right here would calculate the derivative at e, this specific x value. Okay, so e to the e. Well, we know that's going to be e to the x is its own derivative. Plug in e, that should be e to the e. But which of these forms right here would give us that same answer? Okay, well, thinking back towards the formal definition of a derivative, okay, what we did a long time ago to set up the long way to find a derivative is we started with the function, and everywhere we saw x, we replaced it with x plus h. We increased x by some small amount h. It just means we got a nearby point. So everywhere you see x, replace it with x plus h. Then what we did was, remembering the formula, we set up the limit of the secant slope. So we subtracted these two y's and put it over the difference of the x's. These are the x's, the inputs. And of course, we can see that in the denominator, I can cancel the x's. So I'm left with just h. Well, all these choices have just h, and all these choices have as h approaches 0. So the deciding, factor here is going to be the numerator. And you might think that it's a, because we have an x plus h, but notice this isn't an x here either. All right, we're not done though. This is the limit derivative for any x. Well, I don't want to just evaluate the derivative at any x. I want to evaluate the derivative at e. So everywhere I see an x, I'm going to replace it with e. So keeping the limit as h approaches 0 the same, e raised to the, not just x, but e plus h minus e to the e, x gets replaced with e all over h. I think that's going to be choice C. Because I had a specific input value here, I could replace all these x's with that input value. All right, let's see what 3 has. All right, well, if you haven't read through and processed that and begun to think about how you could solve number 3, this would be a good time to shut the video off and read it. Kind of come up with a plan or an idea and then turn the video back on. Because you can watch someone all day long, but until you start to process it, it doesn't really have a lot of meaning and context for you. All right, we have 2 functions. You can graph them in the xy plane in your calculator. Notice it is a calculator question. You can graph them, but the question is, at what value of x do the graphs of f and g have parallel tangent lines? At what values of x do f and g have the same slope? Well, how about find f prime and g prime and set them equal to each other on the calculator? The derivative of f prime, constant multiplier stays there. Derivative is itself times the derivative of the exponent, which is 2. Well, that derivative is easy. Thank goodness it's a calculator problem. Set the 2 derivatives equal to each other. At what x value would these derivatives be the same? I would take the time to put that into y1, y2, set an appropriate window. Find where they intersect. And use the x coordinate. And that's all you're asked to do. Find the x value at which the graphs have parallel tangent lines. All right, cliff note number 18. So you can see the background information provided for this note card. Background information about the natural log function. All good things to know and remember right here. All right, let's look at some examples. Okay, find the derivative of this velocity equation. It's a natural log function, so we know the answer is going to be a fraction. The derivative is going to be a fraction. 1 over, consider this your u, the inside function times the derivative of the inside function with respect to t, because that's our variable. Easy enough, that derivative is 2t. And we would put it on top in the numerator of the fraction. B, all right, a little bit more going on in part B. We have two variable factors. That's going to require the product rule. So this is your f and your g, or your g and your h, whatever you want to call them. This one's pretty basic to where I don't think you need to do the setup and show d over dx. Each derivative is easy to calculate, so I would just calculate them. So it's the first x times the derivative of the natural log, which is 1 over x, plus the second factor times the derivative of x, which is just 1. Little cleanup here, we're going to end up with 1 plus ln x. All right, for example 2, I think we've seen this on a past test, one in class that I've given. And then also, I know this was a few years ago, a multiple choice question that the students had to answer. Find f prime is 0. Let's find the derivative. So the outside function is natural log, so that tells us our answer is going to be a fraction, where we leave the inside function alone. And then we're going to multiply by the derivative of the inside function. Let's just term by term. Derivative of x is 1. That needs to be there. Derivative of 4 is 0. The derivative of that exponential is itself times the derivative of the exponent, which is negative 3. Yeah, we're going to clean this up a little bit. This negative 3 just gets multiplied by this exponential function. So that becomes 1 minus 3 e to the negative 3x over the inside function down here. One minus 3, 4 plus 1, negative 2/5. All right, we're going to, in example 3, write an equation. So you stop right there and you think point slope. If I'm writing an equation for a line, it's got to be point slope. You need x, y, and m. X is 1. I can get y real quickly. Evaluate the function at 1. I'm going to do that first. Natural log of 1 squared is just 1, which is convenient because that's 0. So f of 1 is negative 2. All right, to get m, let's find the derivative and plug 1 in. All right, this term goes to 0. The derivative here. You can apply a property. You can pull the 2 in front if you want, which that might be easier to do. It's not too bad the way it is here right now. So if I'm going to not pull the 2 in front and do a log property, I'm going to do just the derivative. It's going to be 1 over x squared times the derivative of x squared, which is 2x. The x's cancel, you're left with 2 over x. So let's evaluate that at 1. Oh, 2. All right, easy enough. Y plus 2 equals 2 times quantity x minus 1. Okay, that reviewed the natural log function.